Once the radio tracer and its activity have been selected, before performing the experiment, the injection strategy needs to be defined. Let's go back to the example on the measuring the flow rate of a water pipeline during operation. It is important thing to take into account that radio tracer must not alter the flow of the system. The radio tracer should have the same behavior as the bulk flow. Not only is the injection method important, good mixing is also essential to directly correlate the behavior of the tracer with the traced flow. In some cases, modeling and simulation are required. The injection could be continuous or pulsed. In continuous injection, the radio tracer in the form of a dilute solution is continuously injected into the system. The speed of pumping is adapted to the flow speed in order to keep the radio tracer concentration constant. In this case, the injection could even last over a year. The tracer concentration at the detection point is compared to the concentration at the moment of injection. Pulse injection is used in oilfield reservoir tests. In this case, the injection time could take up to several hours, but it is shorter than the time needed for the radio tracer movement between injection and detection. It is very important to understand the mixing process. It depends on many factors: the position, the velocity of the injection jet compared to the bulk flow, the turbulence, the presence of turbines or pumps. Depending on the conditions, thermodynamic formulas are used, assisted by simulation codes. Standard procedures give the basic guidelines for the estimation of a good mixing length and suggest several means to reduce heat. The mixing length in duct flow is defined as the distance beyond which the tracer concentration in the cross-section is almost constant. A good measurement is also assured by a proper test configuration that has to fulfill some conditions. First of all, the time resolution should be enough to allow the radio tracer flow to be tracked. Then, the counts should be enough to give a desired accuracy of the measurement, and in some cases, spatial resolution should be also high. So, a minimum value for the count rate is imposed, and the sampling frequency is planned. The general arrangement of detectors, their position, and the distances depend on the data requirement. This has to be discussed with the process engineers. The unit is divided into different sections of interest, and the detectors are positioned to completely cover the motion of the traced material. The detectors describe the inlet and outlet signal of the different sections. But ionizing radiation is emitted in all directions, so what do the detectors collect? It detects a certain amount of information within a solid angle. The amount of what is inside that angle, inside the so-called detection volume, is not the same for each point. It depends on where the detector is positioned. This information will be taken into account during the interpretation of the acquired data. Then, the experiment is ready to be performed. The solution containing the radio tracer is prepared and its activity is checked. Then, the injection takes place and the detectors start acquiring the counts. The monitoring phase begins. The measurement phase of each probe is defined by the duration and by the counting time. It could range between 1 millisecond and 1 hour, but once the signal has been acquired, there is one final step: data interpretation. First of all, we must consider that the signal could contain some noise, which could be either due to the decay of the radionuclide itself, but also from the detector or the environment. So, the signal has to be corrected. The first correction is for the detection chain response. Some loss of counts could be encountered due to the time response of the detector. This also depends on the dead time of the detector, that is the minimum time required for detecting two consequent counts. Then, the signal has to be corrected for the background radiation that exists independently of the tracer experiment. The radioactive decay correction takes into account the fact that radioisotopes decay exponentially with time. After applying all the required correction, the analysis proceeds with the data elaboration that allows the flow to be modeled. First of all, the response curves are calculated. These are the basis of data interpretation. The time response is the easiest you can think of. It is a graphic representation of the concentration of activity as a function of time. Then, by integrating the time response, it is possible to derive the cumulative response. The cumulative response allows the derivation of several important parameters that are used to determine the performance of a flow. One is the activity recovered within a specific time, while another one is the mean residence time of the radio tracer inside the system. The final time is the time in which the response reaches the background level of the sample. By extrapolating the cumulative response for time approaching to infinity, it is possible to calculate the tracer recovery. In an ideal experiment, the tracer recovered is equal to the quantity injected. However, this is seldom higher than 80%, due to the fact that different molecules are blocked within the system, or go under the detection limit due to dilution, and so on. The interpretation of the response curves obtained gives correct and comprehensive information about the system hydrodynamic parameters. These allow better understanding of the phenomena involved and thus assist troubleshooting or tailoring the system performance.